let us discuss how to solve integrals by substitution. Substitution is a technique for integrals that are more difficult. For instance, the integral of x cosine of x squared dx. And typically this technique substitution applies when we are not able to identify what is exactly the antiderivative, but we identify a certain pattern. So let me right away tell you what is the antiderivative of this function x cosine of x squared, and then I tell you how to find it. So the antiderivative turns out to be sine of x squared times 1/2 plus c. Okay, remember, because this is an antiderivative, there are no limits of integration, we need to add the plus c. Just to double check, show you that this is actually the antiderivative, we can just compute the derivative. 1/2 of the cosine of x squared times 2x. Here I apply the chain rule, we get x cosine of x squared. Okay, so here we apply the chain rule and simplified. Now, when we apply the chain rule and then simplify, it's the same process as if we disassemble a watch and then put the pieces together in boxes. Everything very neat. But somebody that arrives and see the pieces in the boxes will have difficulty imagining how to put the watch together, back together, okay? So that is the process that we are going to do here. The substitution is basically undoing the chain rule. Okay. As a general rule, it treats problems that fit in the following format. They can be written as g prime of g of x times g prime of x dx. Okay, and then you can say that the antiderivative is f of gx plus c. Okay, this is the general format. Now, you don't try to fit it in the format. What you do is, let me show you the steps in the particular example that we were discussing here. The first step is to introduce a new variable. This is what is called the substitution. In our case here, let me copy the integral so that I don't have to scroll all the time. So in our case, when we look at this particular example, we identify the cosine as difficult. And it feels difficult because inside the cosine, there is x squared instead of x. So here, a good candidate for a substitution will be making u equal x squared. Okay, here, this is a bit of an art. It will involve sometimes trial and error, but as a general rule, things that appear inside functions like cosine or exponentials are candidates for a substitution, like here, u equal x squared. Okay, so let me note that because it appears inside the cosine. Okay, but again, you get this by experience. Okay, you just need to do problems and problems and problems, and eventually you develop an eye for identifying the right substitutions. Okay, anyway, once you have your substitution, the next step is to find du. Okay, in this case, it's very clear, u is x squared, so du is 2x dx. So that's a step 2. And then once we have the first 2 steps, we have to replace all x's and dx by use in the integral. Okay, so looking at the integral, we see x cosine of x squared dx. So here, x dx is 1/2 of du. Okay, so we have here cosine of u, okay, because x squared is u, times x dx, which is 1/2 of du. And here we know we are done because when we look at the right hand side, there are no x's left. Okay, if there is any x here left, you are not done. You have to keep going. Now, once we have this integral, now it's very easy to do, right? The cosine of u. So that's the goal of substitution. Reduce the integral to something that is easy for us. So integral of cosine of u du is 1/2 of the sine of u plus c. Okay, but we are not done. We are not done because the original integral was written in terms of x. What we have here is a result in terms of u. Okay, this is the same as if someone gives you a measurement in kilometers and you reply in miles. That person will ask, yeah, okay, but how much in kilometers? Okay, so we need to substitute back. Which means replace u's by x's. Okay, so 1/2 of the sine of u plus c. Remember, u is x squared, so 1/2 of the sine of x squared plus c. And now we are done. Now we can confidently say that the integral of x cosine of x squared dx is 1/2 of the sine x squared plus c, which is what we had in the beginning. Okay, but you saw the different steps here. It is very important to substitute back. I see that in every test that people forget to substitute back. That's the same as filling out a form and forgetting to send it, to submit it. Okay, it will not count. So make sure to substitute back. Let's do one more example. Let's say we have 3x squared times the exponential of x to the power 3 plus 1 dx. Okay, this one is not an integral that is immediate. Okay, and you have probably noticed the difficulty is here in the exponential, right? It's not an exponential of x, it's an exponential of x to the power 3 plus 1. Then once you train your eye, you will identify that this 3x squared is actually helping you a lot here. But if you haven't identified that, you can always try the substitution method. And just try the substitution u equals x to the power 3 plus 1. Why am I picking this one? Because it's what appears here in the numerator and it's bothering me, okay? There could be other choices, but this one works. So let's do this one. So we substitute and then we compute du, which is 3x squared dx. Okay, and this is the reason why I was saying that this 3x squared here helps. Okay, you see, because it appears also in the du. So these two things together is the integral of the exponential of u, that is this part, and then everything else here, everything else is just du. So once we apply the right substitution, we see a much simpler integral that we can anti-differentiate. So here the only step that is left is to substitute back and go back to x's. Okay, sorry, first we need to integrate exponential of u plus c, then substitute back the exponential of x to the power 3 plus 1 plus c. And that is the final result. This method applies, for example, to also the integral of the cosine of x divided by the sine of x dx, which is the cotangent. Okay. In this case, it may not be so easy to identify, but here, if we look at it, probably we think that the problem is that the sine is dividing. Okay, so what we can try as a substitution is u equal the sine of x. Okay, and the way you usually write a problem like this, you just write substitution, u equals sine of x, and then du equal, the derivative is cosine of x dx, which magically appears here too. Okay, so this becomes the integral of 1 over u du. If you don't like this, because you think that was too fast, there is always the possibility you can write, keep the cosine of x here as it is, then the sine of x write u, okay, and then dx write it as du divided by cosine of x. Then there is a cancellation, and what is left depends only on u. Then you know you are done. Okay, now if there are x's left, then you need to try a different substitution because that one didn't work. Okay, anyway, what is the antiderivative of 1 over u? Is the natural logarithm of the absolute value of u plus c. And then the only step that is left is to substitute back. So the natural logarithm of the absolute value of the sine of x plus c. Okay, and that is the result of this antiderivative. This is the antiderivative. Now again, notice that this problem could be a little hidden if instead of writing the cosine of x divided by sine of x, I write the cotangent. If I write it like this, it may be a little misleading because we may feel, oh, I don't remember what is the integral of the cotangent. You're not supposed to remember. You just write it down, cosine of x divided by sine of x, and apply substitution. Okay, so just keep that in mind, that substitution may apply in problems that a priori that they don't really look like they are going to require substitution. Now, always when you do the substitution, make sure to check taking the derivative of what you just did, okay? 1 over sine of x times the derivative of the sine, that is the cosine. One last example. The integral of the tangent. Have you noticed that we have seen the integral of the sine, the cosine? There are so many that we have seen, but the tangent we haven't seen yet. Why is that? Well, this is one of the cases that I was mentioning, that it doesn't look like it requires a substitution, but it does. Very similar to before. Here the substitution is u equal the denominator cosine of x, so that du becomes negative sine of x dx. With this information, we can write sine of x divided by u times dx, which is 1 over negative sine of x dx. Du, sorry. I'm solving for dx here. Now, the sine of x cancels out, and we can write minus the integral of 1 over u du, okay? And this is negative logarithm of absolute value of u plus c, which is minus the logarithm, let's continue here, of the absolute value of the cosine of x plus c, which is difficult to guess for the integral of the tangent. Okay, this is definitely something we don't memorize, we just compute on the spot using substitution.